This is a bracket that's bolted to the steel column, and it's going to rotate about the bolt when it's subject to these two forces here. And the included angle between these two forces is 30 degrees. So the first question says, draw a free body diagram of the pulley and axle. This is a space diagram here where it shows the steel column, the bolt, the pin and everything, but a space diagram just shows the forces that are acting, and you're asked to find draw the space diagram of the forces acting on this pulley. And so you've got, this is the space diagram here. You've got 300 acting down, 300 acting at 30 degrees, and this is the reaction to those two forces there. You not necessarily have to put this reaction in, but it's not bad if you do. So the first thing you've got to do for question 2, when you find the resultant of these two forces, is you can construct a scaled force diagram by just projecting these forces up and up. Right, so you can just project these forces up there accurately, not freehand like I'm doing. And then you use a scale and you can mark 300 scale there, 300 scale there, and you can use a triangle rule like I've done here. You can just draw 300 down there like that, and the resultant will be there. It'll be the resultant. But if you use the parallelogram method, you have to draw this in, this force in down there, and you'll get exactly the same answer. So that will be the resultant. And if you like, if you want to do it accurately, you can use the sine rule. So once you've drawn your force triangle here, it's a little bit more difficult than doing it graphically, I think. You can just put your angles in, and you know this included angle here will be 150 degrees, and these other two angles have got to be half of 30, so they'll be 15. And then you can just use the sine rule to work out the resultant. But as I said before, I think the best way, the easiest way, is to use either the force triangle graphically or the parallelogram of forces to determine the resultant there. Okay, you shouldn't have any problems with that. Now the next question, determine the reaction at the pin, assuming that it is horizontal. So that if you've got this resultant acting through this point here, it's going to work like this. Here's our free body diagram here. So you've got your resultant acting down at 15 degrees, and that's 579.6 newtons. And you're going to have this rotate about the bolt. Now, they didn't tell you that it rotates about the bolt. Oh yeah, it does, rotating about the bolt. But as I said before, they may not tell you that. You have to use your experience with engineering to know that it's going to rotate about a particular part. And so this force here, that force times the perpendicular distance, will try to rotate it anti-clockwise. And this force here, about that perpendicular distance, will oppose it. So that will be rotating clockwise to keep equilibrium. And you can see that it's got a big lever arm compared to that. So this force here will be a lot less than this force here because of the smaller lever arm. Okay, now as you know, you've got a perpendicular distance of 200, but that will be off the perpendicular component, which will be 579.6 sine 15. And so, sorry, cos 15, because it'll be on the base there. And so, because we've got the 15 degrees here, if we had 15 degrees there, it would be sine. So it's cos here. And so we're going to use this vertical component to use this perpendicular distance here. If we wanted to use this force here, we would have to find the perpendicular distance of that force about that point. But it's much easier to use the vertical component. So because the bracket's in equilibrium, you say the sum of the moments about the bolt. Now, sum is sigma here, and that's the algebraic sum because we're using vectors. We're giving positive and negative values to these forces. And so we're going to say they have to add up to equal 0, and you've got to show what direction is positive. So this here, we've got 579.6 cos 15, and I'd work that out. And so put the accurate answer down here. I wouldn't put 579.6 cos 15 down here. Some people do, but it's a waste of effort, I think. And so it's that force, that perpendicular distance time, sorry, that perpendicular force component of the force times the perpendicular distance, which will be 0.2, and make sure you put it in meters here, and that will be negative, close the brackets, and then the other force acting here will produce clockwise moments, so that's the force in the pin multiplied by 40 millimeters, which is 0.04, and you can see that this force is significantly larger than that force there. And that's because of the different lever arm. And so the reaction of the pin is 2,799 newtons. And that, as I said, is much larger than the force that's operating. And they use that a lot in engineering. You should, at this stage, you shouldn't have any trouble with a question like that. That's if you've been practicing these. It's always important to practice these questions, and it's great to be able to work back from the solution so that you can understand how it's configured with the answer and the way that it's set out properly. Make sure that you set your equations out like this. Make sure it looks all coherent. And when we see a solution like this, we think this student is very knowledgeable. Okay, the next question is this. This is a handbrake balance beam. And if you stick your head under the car and have a look at these cables, you'll see that when you pull the handbrake on, if you've got a fairly old car, when you pull the handbrake on, these two cables go to each of the rear wheels. And it's probably a mechanical brake setup. And so when you pull the handbrake on, you put a tension in this main cable, and then it transmits that force to these two rear wheels. So the force equalizing system for a car's handbrake has a metal bar with a cable at each end. The force provided by the handbrake should act at the center of the bar between the two cables. if the bar is moved, so normally this would be in the center there, so you get an equal force on both wheels. But this one's been moved to the side, and it could be as a result of there's something interfering with the position of it in the center. So if the bar is moved 8 millimeters off center, what are the forces in the cables when a force of 1500 newtons is applied to the handbrake? So it's best to just quickly draw a free body diagram and put all the sizes on here so that if it was in the center, this would be 35, but it's moved 8, so 8 minus 35 is 27. And so you've got two unknowns. This whole system will be in equilibrium if we take moments about any point. If we take moments about that point, that point, that point, the sum of the moments will be equal to 0. But it's no good taking moments about this point where the pointer is now, because we'll have 1, 2 unknowns in the equation, and you need a simultaneous equation to work out when there's two unknowns in the equation. So the clue is to take moments about one of the forces that you don't know. So if you take moments about TR, so that's tension in the right, the moment of that force about this point is 0. And so if we take moments about that point there, we'll be able to find that force. I'll just go through that again. If you take moments about this point here, the sum of the moments of all these forces at that point there has to equal 0, because it's in equilibrium. But it's no good taking moments about that point, because you've got a moment produced by that force, so it'll be TR times that distance, and then TL times that distance, and then this force times that distance, and all that will equal 0. But we'll have two unknowns in the equation. So it's silly to take moments about that point. You've got to take moments about a point where it will eliminate the moment of one of those forces. So we're taking moments about TR, and the moment of that force about that point is 0, because the perpendicular distance of that force about that point is 0. And so I've called TL tension on the left, TR tension on the right. You take moments about TR because it's going to eliminate the moment of that force. And so you say the sum of the moments about TR equals 0 with that direction positive. And so we've got here, we've got 1500 times 27. Now I'm using millimeters here because I'm using millimeters there. And you can do that if you know what's going on. You can't have meters there and millimeters there, as you know. So we've got 1500 times 27, and that's going to go anti-clockwise about that point. So that's negative. Then we've got this unknown force, which is TL times that perpendicular distance, which will be 70. And make sure you put it in brackets. And then they have to add up to equal 0. And so we've got TL is equal to 578.6 newtons. So this is 578.6 newtons. Now this force here will be greater than that force there, because this force is closer to it. And so we know that if we can take moments about that point now, if you want, and find that force. But the other way of doing it is probably easier. You know that all the forces have to add up to equal 0 in the vertical direction. There's no horizontal component, so there's no horizontal force in this system. And so that force plus that force has to equal that force. And that's what this statement says. It says the sum of the vertical forces equals 0 with up positive. And so we've found 578.6, which is TR, and that's going up. Minus 1500 is going down, and plus TR is going up. Now, if you get a positive answer with this, you know that TR is correct. It's going up there if you get a positive answer down here. And so you can see that TR will be larger than this because it's closer to it. And so that's how you work out the force when you've got two unknowns and there's a pivot. So it's really important to understand that. Now, the next question here is number 2. Both the cables are phi. Now, make sure that you know that phi means diameter. Phi, and if they don't put millimeters there, which they often don't, you know that all of the dimensions, the units are in millimeters. If they're meters, you'll have an M there. So phi is the diameter. I find the maximum tensile stress in the cable when the bar is 8 millimeters off center. So the maximum stress, you know that stress is load divided by cross-sectional area. You have to know that. You are, as I said last week, you'll be given a formula sheet at the end of the paper in your final exam, which I just finished tonight, which was good. And you will have all of the formulas that you need, but the common formulas like stress, I'd advise you to learn them. They're quite easy. It's just load divided by area. It's the load per unit area. And remember that that means per. And so you write down your formula. Tensile stress equals load over area. Put down your data here. So you've selected this one here because that is the maximum loaded cable. Make sure you put your units there. Use your formula. Don't just put this into your calculator and then put a number down here. We want to see all of this because, as I've told you many times, if you get this wrong and we see that you've made a mathematical error there, you can still get maximum marks here. But if you don't put that there, you will get 0 for the question. Right, so the diameter is 5, so the radius is 2.5 squared. Multiply it by 10 to the minus 6 to bring it to meters squared. If you're using millimeters here, squared, there's 1,000,000 square millimeters in a square meter. Substitute coherently here, keep your equals under one another, and you'll get the answer here. Now, as I said before, you don't need to put that in because that's 10 to the minus 6, and when it comes up to be a numerator, it changes the sign of the index, and so that'll be 10 to the plus 6, which is mega, and you can just write out your answer as 46.9 megapascals. So make sure that you know that there's a difference between force and stress. And if you do this, if you get a piece of paper, let's have a look at a piece of paper here. And you try to pull it apart using a tensile force, just a sheet of paper. You don't know where it's going to break because the cross-sectional area is consistent all the way through. But you put a hole in the paper and it will always break there and there. Try it. And it doesn't matter where you put the hole, whether it's over to one side, you've reduced the cross-sectional area and it will always fail across there. And that's because the area is smallest at the hole there. So if you've got a small area, small cross-sectional area, you're going to have a big stress at that point. And a question like that is often asked in final exam. Okay, look, I hope you understand that. If you want to stay on and ask me any questions, please do so. But thanks for logging on, and I'll speak to you next week.